Okay, hello. Welcome to our joint IoT Hessen, IoT Thüringen meetup with Benjamin KB. I'm very happy that you're, the first 24 people made it. It's nice that you're here. And before we start, Daniel would like to say a few things in German about IoT Thüringen, and then he'll hand over to Benjamin for his talk. So Daniel, stage is yours.
Ja, hallo, mein Name ist Daniel Hendelberg und ich wollte euch im Namen der IoT Thüringen willkommen heißen. Ich vertrete heute den Jonas Hecht, der leider nicht da sein kann. Und ich freue mich, dass so viele Teilnehmer anwesend sind nach so langer Zeit, dass nichts passiert ist. Und ich freue mich auf einen spannenden Vortrag über ein auf jeden Fall außergewöhnliches Thema. And then I will hand over to Benjamin.
Hello, thank you. Yeah, whatever Daniel said, welcome. Welcome to this session. It's great to be, I think it's going to be an international crowd tonight, hopefully. And Diana, when was the last time I was in person in Frankfurt talking to you all about augmented reality, I think, back then, and some MQTT stuff, probably, and open source IoT. Yeah, I would like to say maybe 4 years ago. Tonight it's going to be, yeah. Yeah, and I miss Frankfurt actually, but yeah, hopefully soon enough we'll get back to traveling and so on. Tonight it's also going to be a bit of IoT, a bit of open source, and then I guess I added to my skill set since last time machine learning, and the talk tonight actually is by adding to my skill set. I actually mean it. Like I've been in IoT and open source and software, I guess, pretty much forever. But deep learning, machine learning, AI is something that was really way above my head until last year. Like the math, I guess, behind machine learning, I just couldn't get my head around it. Even the simplest examples about like, hey, here's how you're going to do image recognition with super simple bitmaps, and you're going to recognize digits from 0 to 9 using a very simple neural network. Here's how you're going to do it, and I was like, no, I don't get it. But yeah, tonight's talk is about a very tangible and very concrete, I guess, application for AI and for machine learning, and it actually also has a bit of IoT in it, because at the end of the day, it involves devices, and when you make devices smart or smarter, you end up being able to connect them to IoT platforms and so on. So I think Diana said that in the intro, it's already showing up in the chat. If you have questions, whatever questions, comments, please just drop them in the chat anytime. I might actually try and do some quick show of hands sometimes, so we can try also to keep you all engaged that way. But yeah, please don't be shy, and don't necessarily wait until the end, especially if I end up talking too much and you will have forgotten your question by the time I'm done. But hopefully we'll get through the presentation pretty quick, and we can have a more interactive conversations after that. So building an artificial nose. Let's see. Sorry, I just unmuted the YouTube stream, and I was hearing myself for a second. It was distracting. A few words about myself, if you didn't get a chance to look at the meetup page and you're just tuning in. I'm Benjamin Cabé. I'm a program manager at Microsoft. I've been with Microsoft for a couple of years now. In a previous life, and I guess forever, the way my brain is wired is I do open source, right? And that's also what I do as part of the Azure IoT product group at Microsoft, working on creating bridges and creating collaborations with open source and software and hardware actually as well out there, and try and see how the Azure IoT and the Microsoft Galaxy can benefit from a good open source technology out there, and the other way around as well. right? There might be some interesting open source technology that shines even more when you integrate it with the super broad ecosystem of Microsoft technology, like from IoT and beyond, actually, right? And so yeah, that's about me. You can follow me on Twitter if that's not the case already. And in case, just a quick recap about what we're trying to cover today. Yes, it's an IoT meetup, but we're going to also spend quite a significant amount of time talking about machine learning, and especially in the context of something that at first glance you're like, is it really AI? Like, is that even possible to do and to use like electronic sensors for like smelling and recognizing smells? It turns out that a year ago I was asking myself the same question, and I kind of found some answers. And it turns out that it sounds like science fiction and magic, but it's actually pretty simple. And that's also the goal of today's talk, to be like, hey, just experiment, and you may end up figuring out like and solving problems that you think are super hard, but are actually, like, especially if you leverage open source and so on, are totally accessible, right? And so, neural networks for smells, talking a bit about this essentially notion of TinyML. So we're going to do machine learning and neural networks, but on small devices, the kind of devices that end up powering IoT solutions. So that means that we're going to need to look at and to get a sense of what's going to be the impact in terms of what are the performance we can aim for, what is the cost in terms of energy, in terms of like actual euros and dollars, etc., etc. And we're going to talk about the journey and essentially the behind the scenes of this project of building an artificial nose, because it started with as a silly weekend project on my side, and it ended up being I guess a bigger story that I think is interesting to tell and to share with you all, whether you are like makers and tinkerers at heart, or whether you're just like in the business of tech and like this. Yeah, there are interesting things to say in terms of I guess storytelling when it comes to technology. And then it's an IoT meetup, and TinyML and machine learning is actually something that's very interesting when you start coupling it and combining it with IoT, right? And you make devices, the smallest possible devices, you make them the smartest, I guess, and then you connect them to the rest of the world and to IoT platforms, and all of a sudden you have interesting, even more applications, right? That open up, and things like digital twins and that kind of stuff. So we're going to talk about that as well. In case you didn't figure by now, I'm French. I'm not sure we've actually said that, but you could tell probably from my accent, from the silly photo before. And I do like my bread, right? I've been actually trying to perfect my bread recipe for the past 30 years, probably. And last year, actually at the same time of the year in May last year, like many other folks out there, well, the entire world, actually, I was at home stuck with a lot of time on my hands, and very little flour actually in on the shelves and in the stores. But yet I was trying to perfect my bread recipe, and especially getting into sourdough bread, right? And so using sourdough starter to bake bread, which is actually even more difficult than using yeast, right? And so one thing, so that was that. That was, I guess, something that was in the back of my mind. And in parallel, as part of my day job at Microsoft, someone from Seed Studio reached out. Shameless plug for Seed Studio. They're awesome. They do awesome open hardware. And back in May last year, they were releasing a new Arduino kind of device called the Wii terminal, and they reached out and they were like, "Hey, do you want to build cool demos with our new device? Your Microsoft, your IoT, well, please, like, let's work together." And I wasn't quite sure what to build with the device. Like there's always the sort of the hello world of IoT. You blink an LED, you send the temperature to the cloud. It wouldn't give it wouldn't do justice to neither the hardware nor the breadth of the Microsoft IoT portfolio. So I was like, I need something really like something deeper. And also at the same time last year, and I keep forgetting the name of the person. It's a she. It's the only thing I remember, sadly. We built sometime last year a device which you could call an IoT device, although I don't think it's very much connected. I think it sends SMSs and text messages. It's a device based on Arduino and so on, meant for monitoring the health of a sourdough starter, which is kind of something that I wanted to do, right? I wanted to build something similar. This device, that already exists and which you can find on GitHub and so on. I think it uses a ultrasonic sensor. It's sitting on top of on the lid, essentially looking at the sourdough starter, and it can monitor essentially how high the sourdough starter is to monitor that and hopefully figure out when it's at its peak. And I think it also monitors humidity and so on. But at the end of the day, it's still a manual process, right? It's like, okay, you can get an alert when the sourdough is at 80% of humidity, but what does that mean? Like, is that even good? So what I wanted to do, and I soon realized that it it would be maybe tricky, but I was like, okay, I don't know how AI works, machine learning. Like, I don't really know how I'm going to do it eventually, but I know enough to know that I can potentially train and build a model that would correlate the smell of the sourdough starter with the quality of my bread, right? The input would be using by using gas sensors like there are actually on the market, sensors that can monitor the level of carbon monoxide or dioxide, the level of volatile organic compounds, nitrogen dioxide, and so on and so forth. Take that as an input, right, and track this data, and then bake my bread, right, and then give a rating to the bread. Be like, okay, this bread was super golden brown. The rice was really good. It was crispy, yummy. It's a 10 out of 10. And here's how the sourdough starter smelled like for this particular bread, etc., etc. So that was my idea, right? Trying to leverage the Arduino kind of device, the Wii terminal. So that would be the brain of my device, trying to leverage a pretty neat, actually, gas sensor that is effectively 4 sensors in one. So it's a multi-channel gas sensor. It's also from Seed Studio. It can track CO, carbon monoxide, ethyl alcohol, which is very relevant actually for a sourdough starter, nitrogen dioxide, and volatile organic compounds. And that's what I had. The device, it's effectively an Arduino on steroids. It's a Cortex M4F MCU for those familiar with embedded development. So it has a fair amount of RAM, right? To 200 kilobytes of RAM. It has quite a lot of flash, including external flash. So even like, again, I didn't know much about machine learning, but even if my AI model were to be big, I was pretty confident that I could fit that into the device. And potentially, since the device also has an LCD display, then I could also like do some GUI, right, and some graphical user interface, which I ended up doing. Giving a sense of the cost of the device, right? Because that's I think that's interesting, and we can certainly discuss in more details what you all think. But the device, like, as a it's a dev kit, right? At the end of the day, it's kind of like an Arduino or a Raspberry Pi. It might not be as ruggedized as you want to, depending on your final application, final use case. But for a dev kit, it really does a good job of that. And it costs about $30. It has, again, an LCD and a micro SD card reader. It has external flash, and so lots of cool things. But at the end of the day, like, once you're done with prototyping, it's always important to keep in mind that whatever platform you use, whether it's an sort of an Arduino form factor kind of device or a Raspberry Pi, at the end of the day, if you need something that's cheaper, smaller, that has your very own form factor, what really matters, like the main component in the design, is usually the MCU, right? And so the microcontroller that powers the weird terminal, it's from Microchip, and it's $5, right? When you buy them in significant enough quantities. And maybe these days, with the worldwide shortage of electronic supplies, it might be a different story. But it's good to know that it's pretty cheap, and it's still pretty powerful, like, for a use case. And we'll dive into more details into um, like, what are the actual requirements, what is the footprint of implementing an algorithm for virtual smell. But I can already tell you that half a megabyte of flash and about 200 kilos of RAM, it's actually way more than what you need for just building an artificial nose. It's like you could do with, like, half the amount of flash, half the amount of RAM, and then you would actually cut the price in half, right? You can get the chip for like about $3 in that case. You might not be able to do as much advanced graphical interface if you care about having, like, a fancy LCD display and so on. But, like, in general, just the AI aspect of the solution, we'll see the numbers, but it doesn't need much, right? So I think it's interesting to keep that in mind. So with that, yeah, I had my idea. Like I often say, like, I had an itch that I wanted to scratch, right? And usually, when you like, I wouldn't consider, like, at least until last year, I wouldn't have considered myself a maker, as in, like, someone who builds crazy stuff. Because typically, what is blocking me is that I I'm having a hard time building just for the sake of building, right? And when it comes to experimenting, I need some kind of use case, right? I need an actual problem, not something that's completely made up. And I need an actual problem to solve. And my bread thingy, it's still probably a stupid or a silly problem to solve, but it's pretty concrete. And I knew that this would be a good excuse to dive into TinyML. TinyML being, it's just a generic term coined by the folks from Google working on TensorFlow Lite, the sort of the variation of TensorFlow that targets small devices, mobile phones, and then eventually microcontrollers. So Pete Warden coined the term TinyML, and a definition which is actually interesting is that TinyML is having the ability to run a neural network model at an energy cost of below 1 milliwatt. So what that means is that when you think TinyML, it's really like you're focusing on the inference, like the making your predictions and running your AI models, not necessarily training the models, because this is probably something that happens ahead of time, right? Not on the tiny device. And the prediction, like this run that you make of your AI model, it should be pretty efficient in terms of energy and everything that comes with it, right? It probably also means that it should be efficient in terms of memory consumption, etc., etc. So yeah, don't know if you're familiar with the Great British Bake Off, but ready, set, bake, right? Let's try and solve the problem. And like I said, it's like at the end of the day, I want to build a model that takes, and I want to build some kind of machine learning based solution that takes an input, the smell and the quantity of each gas in the sourdough starter, and turn that into a prediction of how the how good the bread might be, right? And so for that, I need a data set, right? I need to collect enough information to train a model, which model I need to actually build, right? And design like the different neural network layers, and like I wasn't even sure what that even meant back then, but building that, I need some kind of framework to support the solution and the hardware. So the data set, we'll see that it might actually be trickier than, like, I mean, if I am really to build a model of how the smell of sourdough starter relates and correlates with the quality of the bread, it probably means that I will need a data set where I've baked dozens and dozens of baguettes for effectively training the model. So it's kind of, it might be a problem. We'll see soon enough. Building the model, this is where I'm like, no idea what to do. It was really scary back then, and yeah, like I said, like I've tried and I've read many books before, and even like this samples, hello worlds of AI, I just couldn't get my head around it. Framework, I kind of knew that TensorFlow Lite was the new cool kid on the block, and I, yeah, I was certainly looking at using that, but I could use some help. The hardware, luckily, the Wio terminal, the gas sensors that I had, and I had already, I guess, something tangible enough. Like I could already play with the weird terminal slash, like I will sometimes refer to it as an Arduino. I could use this Arduino kind of device plus the gas sensor to already start experimenting and figuring out what the sensors could and could not pick up independently from any like deep learning and AI aspect, right? So enter edge impulse. Like one thing that I guess back in May last year, there were several things happening. Like the fact that I wanted to perfect my bread recipe, the fact that Seed Studio had this new cool gadget, the Weir terminal, the fact that I got some inspiration from the other device that I mentioned before with like the sonar and the humidity sensor. And then there was also this solution from Edge Impulse that is essentially an online tool that really helps when it comes to doing TinyML stuff, all the way from helping you with acquiring your data, labeling the data so that you can like effectively have enough of a data set to train a model, but it also provides some like very helpful hints when it comes to effectively designing a neural network model from the ground up, right? And so that's what I used. And eventually, when you use the Edge Impulse Studio, and we'll probably do a quick demo of that, you end up like training a model and building the Arduino library, the embedded software code that is literally just like ready to use in your embedded application, right? And so that really was, I guess, what what allowed me to start like really getting what a neural network is in the first place, with my data, with my like my problem, my idea, and the problem I actually needed to solve, and not some random sort of like third party hello world, however simple they are. Like the hello worlds of AI, they are super simple, like recognizing, doing image classification with super simple hand drawn digits. It is super simple, but that was like still too abstract, I guess, for me. So first step, if you remember, like we need a data set, we need a model, we need some kind of framework supporting our entire application, and then the hardware. Data set wise, like I think I hinted at a couple of times already, something that, yeah, that really didn't work actually was, okay, I want to train a model that correlates the smell and the health, I guess, of a sourdough starter with the quality of the bread, but I just cannot. There's no way I'm going to bake dozens and dozens of baguettes. So what I did instead is I looked at building experimenting with potentially an AI model that would just classify smells, right? And rather than having to train the model against like my the rating of the quality of my baguettes, I would train the model against some labels, right? Here's a data set that corresponds to the sensor being put on the bottleneck of a bottle of whiskey. Here's the data set that corresponds to the sensor readings for a cup of coffee, etc., etc. And so that's sort of how I pivoted to a slightly different application and use case. And for actually building the data set, a challenge when it comes to IoT or to embedded devices is it's usually fairly simple to collect sensor data. You have all the like you take essentially the sample application that comes with the sensor, and you have your data flowing into your Arduino sketch, your Arduino application. But how do you feed the data? How do you like capture the data and like feed it into your TensorFlow like training algorithms? Do you like store the data somewhere on an SD card on the device, and then like you remove the SD card, you put it in your PC, and you convert the contents of the SD card to a CSV file, and blah blah blah. Yeah, probably that could work, but then this is a typical scenario where Edge Impulse actually helps a lot. So let's do a first demo and a first pose also, I guess. Quick reminder that like if you have any questions, please drop them in the chat. I see there's quite a number of you watching right now. So if there's already questions at this point, please drop them in the chat. And in the meanwhile, I will just show you, I guess, how like the device I ended up building, and then we'll sort of deconstruct like the different steps, especially the AI bits and the IoT bits. So let me share my webcam. All right. So this is the Wio terminal. This is the Wio terminal actually attached to some piece of plastic, which is actually a part of the nose, right? And there's some wires there. So this is the back of the nose. Usually when the nose is fully assembled, it looks something like this, right? You have the nose, the back of the nose, the sensor, like which is usually like attached somewhere right here, a fan that helps suck the air into the device, and a USB cable to provide some power. And then you have a UI right here. You can leverage, and I am leveraging the different buttons of the Wio terminal to be like, hey, on this screen, you may be able to read the like the raw sensor readings. Right here, there should be a graph. For some reason, it's not showing. Yeah, there it is. So this is the real-time like chart of the different sensor readings. And what else do we have? And then we have another, like right now we are in training mode. We'll see later what that means. Right at the top of the screen, it says that we are in training mode. And it actually says on that screen, hey, you're in training mode. So if you're interested in collecting training data for, I guess, training your model to smell and the nose to smell new things, please use the Edge Impulse command line. So we may do a quick demo of that one. But in the meanwhile, what I'm going to do is press the blue button right here to switch to what's called inference mode, right? And right now, the sensors are still like the device is still collecting sensor data. But when I'm going to take the sensor
Benjamin,
and actually, yes.
Sorry to interrupt, but somebody just asked if you could show those physical things a bit slower because there's a delay and it's kind of too
Okay, I'll
fast.
do my best. Yes. Oh yeah, I can see that it's not super fluid on the stream. I'm actually, yeah, I'm wondering if I could, let me just quickly see if there is, let me try that one. Let's see. Hopefully we'll have slightly less delay. But yeah, so this is a can of coffee, decaffeinated coffee, straight from Italy. It actually smells really good and really strong. So what happens if I put the sensor within the box? I'm actually going to put the lid on to make sure that the sense really make it to the sensor and then back to the actual sensor. Let's see. Right here. So right now it's still reading ambient. But slowly it should switch to smelling coffee. For some reason it's quite slow tonight. But yeah, now it's pretty confident that it is smelling coffee, right? So that's what the device does. It actually, like if I were to grab a bottle of whiskey, which don't have around actually, which is probably good to not have whiskey at your desk. But I could also show you that the model is also trained to smell that, right? And uh, just if I don't know if you remember what were the readings before, but like you can actually see that the pretty much all the gases that they went like the amount of NO2 and CO, etc. They all went through the roof, right? Because it's I mean it's smelling coffee, so it's pretty strong. One thing that I will do to help maybe with the let's see, I'm gonna do that. I'm gonna try and help with the frame rate, hopefully not breaking things. Hopefully it'll be better then. So yeah, that's what the device, that's what I ended up building. And I actually had this up and running in very little time, right? So I will actually now dive a bit deeper into some of the aspects of the solution and mainly the machine learning model actually. So let's see. I'm just having a quick look at whether the video is slightly faster now. Doesn't look like it's much better, but and it's pixelated too. Let's see. We'll see at the next round of demos what happens. Switching back to my demo. Looking at the question from Adalberto, is there a tutorial when I can learn how to set up my Wii terminal to run this application that you are showing us here? I will let Diana, maybe, I hope, Diana, you have the link to the GitHub repo handy, but you can already drop that in the chat maybe, because even if I were to drop it, I'm not sure I can post links. But yeah, there's actually lots of instructions on a GitHub repo that I put together. So yeah, you may want to have a look at that. And a question from Abhijit: how does the sensor reset to smell new smell? I think this is the next part essentially of the talk, which is great. And hopefully we'll answer your question by keeping, but yeah. Looking at the rest of the presentation, how can a machine smell anyways? Because that starts with that, right? Even before talking AI, like those readings we could see on the on the display before. How does that even work? How does the gas sensor even work? I don't know if you're familiar with the term MEMS, but it's essentially a micro, like the sensors that we're looking at here, like there's four of them. Those are super tiny micro mechanical kind of sensors, and for when it involves gas, it's effectively an electrochemical reaction that, and depending on the gas, you would have a different semiconductor, a MOS, a metal oxide semiconductor, that is like there is a tiny thin layer of it embedded in the sensor. It gets heated, so which means, by the way, that the sensor requires a fair amount of current to work, at least more current than what you might be used to for other sensors like humidity or temperature. And so there is some, the sensor is being heated up, and then there is a chemical reaction happening with the ambient air and with the molecules in the air. And this chemical reaction is nothing more than an oxidation reduction. And so you have some like electrons being removed from the thin layer of metal oxide, and that causes a change in resistance of the sensor, right? And depending on whether it's an oxidation or a reduction, the resistance will change. Like we will either increase or decrease, but at least once you have calibrated the sensor, then you can get a sense of, okay, I'm interested in VOC with 10 parts per million of volatile organic compounds, VOC. I know that's what the data sheet of the sensor tells me. I know that I'm going to have a reading of 100 ohms. For a higher concentration of volatile organic compounds, for example, when I smell coffee, it's going to be 1,000 parts per million, and then the resistance is going to be different, right? And so that's how it works, and that's the kind of data that I'm effectively going to be collecting, right? Turning this resistance into an actual voltage that I read through the analog inputs of my Arduino/Wio terminal device, and then getting data, right? Abhijit is asking whether the project can be done using BME from Bosch, the BME 680. The answer is yes, and that's actually an interesting one. We'll talk a bit about I don't think I've said it already, but I might say that a couple times during the talk. This project, it depending on how you approach it, it sounds like science fiction, but I also actually like to call it a very low tech kind of like DIY project. Like I'm really using off the shelf sensors. The sensors I use, they like even on their data sheet, they actually say like in bold characters, um, those sensors are good for measuring relative quantities of gases, but please don't take the readings as being absolutely correct, right? As in, if you take one sensor, you buy two sensors from the same manufacturer, the two of them might give slightly different readings, right? They are kind of calibrated, kind of accurate, but probably not enough for some industrial applications. And yet, with machine learning and with what's called sensor fusion, you can get really good results. Like you can take the sensor I used, and to answer your question, Abhijit, yes, you can use, for example, the BME 680, and you can either replace the sensor in my current design, or probably better, you actually add another one, the BME 680, which also reads VOC, which probably reads VOC with a slightly different like pattern. It might pick up different kinds of volatile organic compounds with different accuracy, different resolution, and that's goodness because that's more input to train your model, right? And so, and I was referring to low tech also as in, yes, the sensors are cheap, but if you need better accuracy, there's nothing that prevents you for trying to find better sensors out there and to train more complicated models, right? That take more inputs into account. So the sensor readings, the raw sensor data, essentially what I needed to do is collect just enough sensor data that I could like have a good be reasonably confident that I had captured the fingerprint of a given smell, label the smell, let's say that's the smell of whiskey, and then try and feed that into some kind of machine learning model that I would build. I don't really know how, but then that's where the Edge Impulse Studio helps. It effectively helps you with the first step of machine learning, which is usually doing what's called feature extraction, right? Making sure that your raw data, you actually start tweaking it and cleaning it up so that you extract meaningful information, right? And so my gut feeling, although I had no idea like what the math around that would be, was that, and also looking at the chart, right, like that we saw before, looking at the graph of the different gases going up and down as I was moving my sensor, I was pretty confident that what I needed to capture were things like, for say 2 seconds or a second and a half worth of sensor data, the min, the max, the average, the slope of the sensor readings, those all were important information, right? If I'm putting the sensor on top of a bottle of vodka, like I could see with my own eyes without needing AI, I could see that the alcohol sensor was going through the roof and was going through the roof way quicker than it was when smelling whiskey. So that was interesting information, right? But if I look at all those numbers here, it's not like super clear that the information has been properly extracted, right? So first step was to and that was where I guess again my gut feeling, my intuition was to be like, okay, I think capturing about 15 samples of data, like at 10 hertz, capturing like 15 times the readings of the sensor, that should be enough information. I don't think I need more, because otherwise I will introduce latency in how fast my model can pick up new smells. And if I capture less data, it's unlikely that I will have enough to capture the full fingerprint, right, with the slope, etc., like I said before. So this data, first step is to flatten the data, right? Make sure that it's actually structured in a way where you actually see that you have first the NO2 and then the CO level and then the volatile organic compounds and then the nitrogen dioxide, whatever, the one that I forgot, the ethyl alcohol, and then make sure that this is all lined up correctly, then making sure that it's actually scaled to a number between 0 and 1, because that's something that the Edge Impulse Studio helped me figure out that helps with making the model easier to train. And then you have the data, and then you actually do the feature extraction. And in Edge Impulse, it's effectively just one click away. It takes your data, like you have your raw data, and feature extraction might be many things. Like if your data is images, then you might want to go like a specific path. If your data is audio or is something that's along the lines of vibration from a piece of industrial equipment, or like things that really have a strong time and temporal aspect to them, then you might be interested in doing feature extraction through running FFTs and things like that to try and extract the main frequencies, the main patterns in your periodic signal. In my case, there's no periodicity to it, right? What is important is more things like, for each sensor, I want to extract 5 key elements that my intuition was actually telling me that those would be important: the average, the mean, the max, the root mean square, and the standard deviation. Essentially, in a nutshell, capturing how strong, right, and like how strong and what was the volatility also to some extent of each sense, right? And once you have that, then it's actually machine learning as usual. the kind of machine learning that I didn't quite understood as of last year, mainly because I couldn't really get this feature extraction part. But now that I had that, it was clear in my head, and I would actually be curious to hear if it's clear in yours as well in the chat. What was happening is that now I had my raw data. So my raw data was, let's see, so 1.5 seconds at 10 hertz. So that's 15 samples for my 4 sensors. So 60 numbers, if you will, 60 weird numbers with like no clear information visible in them that were turned into 20 numbers, right? 20 characteristics for each of my 4 sensors. That would be the average, the min, the max, the root mean square, and the standard deviation. And some of those numbers might be like, yeah, higher than others. Some of them might, and at least I was pretty confident that all of them, one way or the other, they were capturing the information for each smell, right? And so those are the 20 inputs that you see to the neural network. And then I was looking at training a model that would like essentially solve an equation, right? It's a function. You call the function with those 20 characteristics, and you want it to tell you what is the level of confidence for each smell that it's been trained for, right? In my case, that was three smells. Is this the smell of ambient air? Is this the smell of whiskey? Is this the smell of coffee, right? And training the model essentially means finding the right settings, right? So that for a particular input that corresponds to, say, whiskey, most of the the flow of data, or like I mean the flow of things that go through the neural network end up being mostly targeted towards the say the first neuron there, the first output of my neural network, essentially signifying that the this would be ambient air, right? And so that made things more tangible to me, and I was able to train the model come TensorFlow Lite, right? And so the once I had the model trained, and I will actually show real quick how it looks like in the Edge Impulse Studio, because I think it's interesting to have a quick look at it. Let's see. Let's open the Edge Impulse Studio. Essentially, what's happening is that you can pretty easily, and I will go really fast, so I apologize for that, but you can check out again the GitHub repo and or the Edge Impulse documentation as well for what it's worth. I have my so my weird terminal device is still it is back in training mode. If you remember from earlier, it's back in training mode, and that means that if I look at what it's outputting on the on its serial console, that's what a weird terminal, an artificial nose in training mode means in my world, I guess. It means that it's just like dropping the sensor readings on the serial console so that you can do something useful out of them, potentially from your desktop computer, right? Which is exactly what I'm going to do. I'm going to launch and run the so-called Edge Impulse data forwarder, which effectively ends up connecting, like virtually tethering, if you will, my artificial nose to the Edge Impulse Studio in the cloud so that I can actually acquire data, right? And it can be like, hey, I would like to acquire 2 seconds worth of data. And since the sensor is just like hanging out in the air right now, let's say it's so I have a new sample, right? And that was as easy as that. And I can potentially import data that I have from other devices, from existing CSV files. And then once I'm confident that I have enough data, I can start building my model. And like I mentioned before, it's actually pretty straightforward. So here it's already been done, but what I was referring to earlier, right? Depending on whether the data is slow moving averages like temperature data or gas sensor readings, maybe you're going to use the flattened block. If you have an image, you might want to use that. If you have an audio signal or you want to do spectral analysis for detecting vibration, detecting the frequency and the power characteristics of a signal, you may be interested in using a slightly different form of DSP. But all of that, like it was, like I was very much guided into in the process in the studio, and so eventually I built the model, I built the neural network, trained the model, and eventually you get to a point where you can build an Arduino library, which is essentially the actual model, the like the whatever are the all the right parameters so that the model can tell ambient from whiskey, from coffee with reasonable confidence. And so it's the model, but it's also the TensorFlow Lite framework. And so what is TensorFlow Lite? And I'm going to quickly go through that and then catch up on the chat because I see lots of questions there, and I'd actually like to take them as they come. TensorFlow Lite for microcontrollers, it's essentially just an embedded library, right? That's meant for allowing you to run and to do inference right on microcontrollers, and it's designed to work offline, right? Although we'll see that the device eventually ended up being an IoT device, a device that's connected, but it's like initially you certainly don't need any form of backend server. Everything happens on the device itself. No connectivity. Everything is optimized in terms of size, in terms of power consumption, and everything is optimized also in terms of performance, which also means that more often than not, especially for ARM-based devices, there's usually some hardware accelerations that can be benefited from in the ARM Cortex space. You would have libraries like CMSys NN for neural networks or CMSys DSP, which are effectively routines that try and leverage the actual silicon whenever possible to run faster for all those operations that are typical for neural networks and like all those matrix manipulation and so on. And it helps with performance. It helps with code size as well, right? Rather than having to bring in custom C code, you can actually link to like functions that are implemented in the actual MCU itself, right? So yeah, I think I said that the TensorFlow Lite for microcontrollers runtime is available and nicely packaged as an Arduino library, and sort of by design, like it's only a subset of classical TensorFlow, right? So if you have an existing TensorFlow super complex AI and like neural network model for video, like real-time video analysis, it probably it's just not portable to TensorFlow Lite. You may try, like if granted that the size is not a problem, you might actually be able to port it. Like if some of the operations in TensorFlow Lite are not supported, you can actually write your own implementations if needed. So let's try and catch up on the questions real quick. Michael, back to the discussion on the BME 680 sensor. Yes, having the sensor as an addition would be awesome, right? Like the more input, the more sensor fusion happening, the better for accuracy. And then what did we have? Michael, does the reading stabilizes? Yes, really good point. So the question from Michael is back to the discussion earlier around DSP, around trying to extract things like the minimum, the maximum, the average of like each sensor readings. the question from Michael is, but after some amount of time, the sensor reading will have stabilized. Yes. So what I tried, and it was nice actually to see that my intuition was confirmed and was something that I could implement in the neural network. During the training, I tried to capture both, right? I tried to capture, hey, let's put the sensor on top of the bottleneck of whiskey and let's capture the data, the training data straight away. And that's going to be, yes, that's whiskey. That's maybe a slightly lighter version of the smell of whiskey, but still, let's label it as whiskey. And then 10 minutes later, let's also do another round of capturing, of data capturing. And this time around, it's going to be way more stable. And that's also going to be whiskey. And let's also capture that in the model. And if you build your model well enough with just enough hidden layers in your neural network to capture just enough information, you should be able to train the model so that both we are getting to whiskey and, oh, this has been whiskey for the past 10 minutes. Both those characteristics you capture and both are whiskey, right? And you can even trying to capture different setups and different conditions really helps, right? Also trying to perform readings indoors and outdoors, or perform readings when the weather is super humid, like all of that, it helps to capture all those subtle variations, right? Francis was asking, why would you need neural networks for the feature extraction? Feature extraction is not happening through neural networks. It's just good old statistics. But you guys answer each other's questions. So that's actually perfect. If there's more questions, please keep them coming in the chat. I think I said in the intro that I wanted to touch a bit on the a few figures and a few numbers to have in mind when it comes to performance, to code size. At the end of the day, the model that I ended up building, so I did several variations. Whiskey and coffee is kind of my go-to demo, but I've had really good results trying to classify spices like za'atar from white pepper, from black pepper, from cumin, I think. Like those are all like different enough, I guess, that they can be captured in the same model. And so for a model that can pick up 3 to 5 smells, then the architecture would be like this, right? You don't need more hidden layers. You don't need more inputs. So the model at the end of the day is a pretty small one, right? It's a model that fits in 3 kilobytes of code of Flash, and then the full blown, like the full TensorFlow Lite framework is about 27 kilobytes. Well, actually, I shouldn't say it's the full TensorFlow Lite framework. It's only those bits of TensorFlow Lite that are needed for my particular model. So that also helps with size optimization. It doesn't really use a lot of RAM. 4 kilobytes it's okay. It's a lot depending on how the kind of MCU you have in mind, but at least it's plenty for the Wii terminal. And the performance, since at the end of the day, like the neural network is not that deep and not that complex, it's not that many operations that need to happen when you want to run the DSP and then run an inference. It's like you can do everything in about 1 millisecond, which leaves plenty of time for doing the data sampling, right? Like I need to sample data at 10 hertz. I want to like read the gas sensors every 100 milliseconds. But I mean, that's like I have plenty of time to do that. Should I want to optimize my model further, then you could look at quantizing the model. So I won't go into the specifics of what that means, but essentially, by default, a model like the the equation, like I described it earlier, the equation that captures what is the correlation between the gas sensor readings and ambient whiskey and coffee. That equation, usually, like by default, it would be like all the parameters would be stored as float numbers. You can actually do use some tricks to pretty much keep the same accuracy, but only using like short integers. So that helps. You can improve performance and code size even further by using the CMSys libraries, like I mentioned earlier. And Edge Impulse also has something that they call the Eon compiler, where you can actually get rid of TensorFlow Lite altogether, rather than having your embedded code loading a TensorFlow Lite model in memory and then sort of interpret the model to do some TensorFlow Lite operations. You can actually like take a shortcut and directly compile into native code, which is something that the Edge Impulse Studio does, and that can help a lot actually with the footprint. Hey, Arijit, great to have you in the chat and watching the session. Something that I didn't mention, and I think that's something that's interesting to have in mind, especially back to my point around low tech. Like I've tried to be pretty clear since day one that this project looks really cool and looks like sci-fi and looks like it's solving lots of problems. I would hope it is, but it's still pretty low tech. It's using very like basic gas sensors, and the way I think like all of us as an industry, when we do anything that's remotely marketed as AI, machine learning, artificial intelligence, blah, 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 we need to be clear about the expectations, right? And we need to have some ethics, I guess, about that. And that's particularly true for the use case and the application of using AI for smells. This is effectively a neural network that does classification. And so that's an equation, like I described it earlier. You give an input, it gives you an output. You give an input, which is the characteristics of the smell of strawberry. But with the model that we saw earlier, it has no idea about what strawberry smells like. So it's going to try and find some solution. It's going to be like, strawberry? Sure, it's 51% similar to whiskey, I think. Then you smell honey and same problem. You're like, hey, sure, 78% coffee. It seems similar that I only know about whiskey, coffee, and ambient air. So this is coffee. So one thing that's important to add, like both, like I mean, from I guess a software perspective, but also from a UI, a user interface, and a user experience point of view, is make sure that you have an anomaly detection algorithm in place for the nose. That is effectively an algorithm that does very simple clustering kind of things, and I can actually show maybe in the Edge Impulse Studio what I mean by that. The idea is to train a very simple clustering algorithm to capture the essence of how the training data looks like at a very, very high granularity, but just enough so that later on, when you try and smell something, if the input is outside essentially of those blue circles that you see, then this means that the neural network will give you a result, but the anomaly detection algorithm will be a hint to be like, oh yeah, sure, I have a result, but I should take it with a grain of salt because it looks like the data is nothing like I've seen during the training. So I don't think I can trust the readings, right? So that's that's important to have in mind. And I mean, in the context of the nose, it's actually something. Let's see if I can show it real quick. If I share my my webcam again, the way I show it on the device is by means of the smiley face on the right hand side. Like right now, it's not only the neural network is confident that it's ambient, but the anomaly detection algorithm is confident that this is data that looks very much like something that's been seen during training. Now I actually have a bottle of ethyl alcohol right here, like raw ethyl alcohol, something that's really, really strong, really smelly. What happens if I put my sensor on top of it? Let's see. I need an assistant, but it was actually working. Let's see. See what it says? Yeah, it's whiskey. Of course, there's tons of alcohol. It has to be whiskey. Like out of the things the model has been trained on, whiskey, coffee, and ambient. Probably the closest thing from ethyl alcohol is whiskey. But anomaly detection wise, not so much. It's probably not whiskey. Don't drink it. So yeah, that's actually glad the demo worked. And let's switch back to the slides. And let's make sure we don't also go too much over time. But yeah, I think that was an important point and an important aspect when it comes to setting expectations, I guess, when you have AI involved. Demo wise, I think I've done all the demos that I wanted at this point. Then a few things. One is, I think I mentioned in the intro, it started as a silly weekend project, and then eventually it was more. It was more in terms of like designing the actual enclosure, and then in terms of like it actually took off on the internet, and I was surprised by that, especially since it's such a low tech kind of project. So I think there's a lesson in there for all of us in terms of we all, one way or the other, and it's hard to tell actually because we're not in person, but all of you in the virtual room, you are software developers, you are folks who work on bleeding edge IoT, embedded AI in your day-to-day job. And sometimes, like we don't necessarily realize that, like the rest of the world might not have caught up just yet on what are even like the applications of some of the, like even I didn't know about like AI. I wasn't approaching AI and machine learning as something that would be so easy to apply to gas like gas sensors and to and that I could actually build a model for predicting and for classifying smells. And so like I said in the intro, I'm sort of an open source person, so I documented my journey like on GitHub and like always in the open. And and the project has been pretty popular, and it's been interesting to see, like to talk with folks who thought about applications for this device and for this solution that I didn't think of initially. Like for me, initially it was my stupid bread idea, but then I was like approached by folks suffering from anosmia due to COVID-19, especially. They lost the sense of smell. Such a device, and especially if it's open source, open hardware, that really helps them, right? So yeah, I want to briefly talk about that, not because it's a me story, but just because hopefully there might be a bit of like potential inspiration in the way you you talk about the various projects and the various tech that you're working on. So some name dropping of the technology and the projects and the software that I ended up using in my journey. Of course, I mentioned the Weir terminal and Edge Impulse TensorFlow Lite, but I also learned some Blender. Blender might not have been the best tool for building the enclosure, but that's how I ended up building the thing. I took a 3D model on not on Thingiverse, on Sketchfab. So it took an existing 3D model, and then ended up tweaking it so that it would become like an actual enclosure. And I did a live stream, and I ended up making the actual box open hardware. So if you guys are interested in 3D printing the thing, please check it out. And then I did some, so that was back in earlier in February this year. I did some silly tweeting about the project. And again, like, and I do mean it, I really don't think it's rocket science. I really don't think it's anything specific. But like, I tweeted about the thing, a silly animated GIF with like just the device smelling a cup of coffee, and it went viral, right? And it went like literally viral, and so that was really sort of a realization for me, because I'm in my day job, I work on bleeding edge stuff, and to some extent I have to make sure that folks know about all the bleeding edge stuff and all the cool stuff that Microsoft is doing in terms of IoT. But there's also sort of like, sometimes you need to go back to the basics, right? And the result of this project is super impressive, but hopefully the way I deconstructed the neural network and the how the electronics works within this project, like hopefully you've realized by now that it's pretty much an empty shell, that there's not much, but telling that story has been super impactful. And I ended up being and writing an article in Make magazine, which is not like, I would actually encourage you to buy the latest issue of Make magazine, or if you wait a couple more weeks, I think the article that's in there will be freely accessible. But it actually dives a bit deeper into how you can replicate the setup, actually probably more than what you will find in the GitHub repo. The GitHub repo is mostly about the source code and the 3D enclosure. The Make article is even more didactic. And then, yeah, the project was featured on Mashable and a bunch of other pretty popular websites, which was like, I like, it's really cool, and I still feel very much like an imposter, because at the end of the day, again, I don't think it's rocket science in any ways, but hey, it's cool. I think, yeah, no, what I wanted to show here, I think I've said before, so it's like this, yeah, this notion of the anomalies. I think it's really important to keep that in mind. If one way or the other, like you touch AI in your day-to-day job, or in your day-to-day hacker projects, keep that in mind. Like, how do you build an interface that sets the expectations right to the end user? And then last but not least, it's an IoT meetup, and I've been talking about something that I don't even know much about, which is machine learning and AI. But I hopefully I pretended right. IoT, like, one thing that I think is really interesting with the use case of a smelling device and a smart smelling device is when you actually think about use cases like restrooms in an office building or in a conference center. You may have a gas sensor, such as like the one we've been looking at, deployed and stuck in the ceiling of the room, right? And it's stuck there for good. It's not like you're going to have, you don't want to go there and look at the LCD screen to be like, oh yeah, it smells nasty in there, we better clean the room. No, you actually want the device to be there to smell and detect when it smells funny and when it smells nasty, and then send some kind of alert, right? And this is where you build and you add, you turn AI into AIoT, like some folks say, right? So you have the intelligent nose, the smart nose at the edge, and then you add the internet on the other side. And then, if I were to simplify very much, then and actually the weird terminal, I should have mentioned that, but the weird terminal, it's Wi-Fi capable. So we're going to leverage that in a moment. But yeah, one thing that comes to mind is, okay, if I'm able to connect my device to an IoT platform, it means that I might be able to send, well, first the inference results to the cloud. Things like, hey, it smells nasty, 92%. It smells like fresh air, 98%, etc., etc. Might even send the raw sensor data. It might be relevant. It might be useful if you want to collect that data in the cloud so that you can train your models further, right? That could be a benefit of having IoT capabilities there. And it's two ways, right? As soon as you have connected a device such as the nose to an IoT platform, you can also talk to it, send commands. Commands being very likely things like, here's a new AI model for you. A nose, out of the box, out of the factory, you knew about fresh air and you knew about I don't know, like dirty air. But then here's a new model that's way more specific. Here's the model where we have we can pick up new scents, and you can detect when the restrooms smell like COVID. I don't know, like there might be sensors that can pick that up. Probably not, maybe not. I don't know. You tell me. But I mean, you get the idea, right? You can reprogram completely over the air, reprogram the device, and then well, I'm actually going to show a demo of that. So I'm going to reboot the device in a specific mode. So let's see if I can actually try and not have to hold my camera. Yes. Okay, so let me share my webcam again. So the device, it looks kind of dead right now. It's not, but it looks kind of dead. Oops, let's see. I want to do something real quick before jumping into the demo. So essentially, the firmware, like the application that we've been looking at until now, it's really good at smelling stuff, but it's also capable of connecting to an IoT platform, right? And so we have, let's see, let's make sure. Why is it showing? It shouldn't show this one. We want to connect the nose to an IoT platform. The platform, in my case, I being Microsoft, like I quite like Azure IoT Central. So essentially, Azure IoT Central is an IoT platform running in the Azure cloud, which is like super easy to deploy, and that takes care of like providing you with a way to send and am I actually, I'm not sharing my screen right now. I'm only sharing, sorry. I guess I will have to jump between my webcam. Sorry, I thought I was showing you that. Apologies. I want to connect the device to Azure IoT Central. So I've already set up essentially my environment and my dashboard for hosting eventually thousands of noses, right? And so I have a bunch of them that are actually simulated right now. So it's as if I had nose 002 sending data into the system, and the data I can have a look at here in my dashboard. I can maybe implement some rules so that when something happens, I send an SMS. I can offload the raw data that's being captured, store it into a database so that I use it later on for training my models. But probably what I want to do now is actually connect a real nose, right? And the way I'm going to do that is that I could probably, if I had time, I could have implemented some kind of workflow similar to the way you onboard an Amazon Alexa or a Google Home device in your home, right? You have the initial pairing / provisioning process, and so I could probably do that from a mobile phone application. Here, I'm going to do it from the command line, but it's still going to be pretty straightforward. I have initially the first time I to deploy the device into the ceiling of the restrooms, I need to make sure that I configure the Wi-Fi. Let me get the window because I think I have some background noise. There we go. Yeah, I would configure the Wi-Fi, and I would configure the credentials to connect to Azure IoT Central. So the Wi-Fi, it's already there. I don't think I will touch that, but the credentials to connect to Azure IoT platform, I'm going to put them here. And actually, I should have done something slightly different. I will make sure that it's a unique name. It's going to be IoT Hessen demo. What I just did is flashed into the the firmware, flashed into the device. Sorry, the its credentials, right, so that it can connect. Like next time it reboots, it will connect to Azure IoT Central. So the device is now going to reboot. And let's see, yeah, that's actually better that way. So device is now connecting to my home Wi-Fi, connecting to a time server so that it knows what time it is, provisioning to Azure IoT Central. Oh, did you see what happened in the background? IoT Central is telling me that a new device is there, right? And so I guess we're back to the IoT hello world to some extent. But what's really cool is that it actually works. The device is what we call plug and play, right? It just connects, it just shows up already as a nose, right? It's not just a device sending random raw telemetry data over MQTT and whatnot. It's actually sending meaningful data that directly ends up in a dashboard. It's already exposing a setting like out of the box. The device, if I go there, yeah, the telemetry interval for a brand new device, it's set to send the sensor readings every minute, which I don't like for a demo. For demo purposes, I can switch to 2 seconds. And now let's see, if we go back here, we have the device that rather than communicating every minute, it should communicate every couple seconds, right? And now if we look at the chart, it's it's reacting way faster. And even like the inference readings, if I go back here, if I switch the device to inference mode by pressing the button, then it's also something that's being sent over the air, right? And then I don't think I need to do the rest of the demo, but you get the idea. You can maybe implement some rules, right? If NO2 goes above X ppm, do something. Or if it smells like coffee, which is more something that actually uses the AI. If it smells like coffee, then send an SMS to say, hey, your coffee is ready, kind of stuff. So that's the benefit, or I guess, or like the idea of connecting to an IoT platform. And last but not least, next step, and it's also something that's possible in the Azure IoT ecosystem, or like, I mean, several IoT platforms out there are now getting to the point where they enable you to build, to go from connected things to connected environments, aka digital twins, which essentially means back to the smart building, smart restrooms kind of use case before. What happens when you have your IoT cloud platform? A graph, a knowledge graph of, I mean, I'm in real estate. So for me, like my world is all about cities and blocks within the cities and buildings within those blocks. And those buildings, they have different floors, they have HVAC systems, they have all sort of things. They have people who are responsible for the cleaning and the maintenance of the buildings, like here for Tribune Tower, it would be John, etc., etc. And then at a given point in time, in that particular graph, you may have a twin a digital representation of the physical nose device that's attached to floor number 3. So then what happens when said nose says foul air and sends that information to the IoT platform, you can then route the data to the digital twins graph and then act on it, right? And then navigate the graph to be like, oh, okay, today, if the nose is in floor 3 in this particular building today, like this afternoon, it's John that we should text. And you text John and you ask them to go and do the servicing of the room or do whatever, right? And you have this dynamic sort of aspect of the solution. So that's digital twins, and that's something that's capable. That's possible to do with the nose and with everything that's actually on the GitHub repo. So I would encourage you guys to check it out. The GitHub repo is there, github.com/cartband/artificial nose. It has all the source code, all the bill of materials, the 3D designs, etc., etc. Some reading suggestions. I should have dropped the ISBN numbers or things like that, but just Google O'Reilly, TinyML and O'Reilly deep learning, and you'll find those books. And there's plenty more out there, but those are really, really good ones and written by actual experts. And this is how you would find me online: Twitter, my blog. I am to blog about the project. I should, but there's also plenty available on the GitHub repo or in the Make Magazine article, and there's other interesting things on the blog, hopefully. And I think that's what I had. I only went 20 minutes over time. It was still bearable for you all, I hope. Diana, can you help me with all the questions that lined up, maybe? Or I can try and rewind the chat, but it would help if you took notes, maybe.
Thank you very much, Benjamin. First, thank you so much for the great talk. I really enjoyed it, and I think so did everyone else. So a big round of applause without being able to clap, actually. It was great, and I think you're being too modest about the project. I think it's awesome, and I think part of the magic of this project derived from the fact that the sense of smell is something so complex that people, even I, can't imagine a machine smelling things, because it's just a too complex thing. Computer vision has been around for a while, but smelling is it's a life-saving sense as well, as somebody also wrote in the chat. And I think we've known each other for 8 or 9 years. We met back in, I don't know, 2012, 2013.
11, probably.
Yeah, it's been that long. When you were just starting the Eclipse IoT, or back then it was called M2M working group. And no one would have imagined anything like this 9 or 10 years ago. It's pretty amazing. About the questions, I wrote down 2 questions that were asked earlier. They weren't answered explicitly, but I can imagine they were answered in the meantime by your presentation. So Michael asked, can Edge Impulse also be used to just capture the training data, export it, and use it to train a model somewhere else?
Yes. Short answer is yes. Long answer is at any time, if you feel more comfortable manipulating, writing some Python code to build the model with Keras and whatnot, you can effectively get the data off of the Edge Impulse platform, download a Python notebook, and do the training wherever it pleases you on your local machine or on another cloud. Yeah, that's totally possible, and that's actually what I like about Edge Impulse, and what makes me feel like I don't feel bad. Like talking about like how much I like Edge Impulse, because like at any point, if you're not happy with their service, it's TensorFlow, right? In TensorFlow in Python, you just get you use the tool wherever it helps or you feel it helps you, and then wherever you feel like you want to have more control, it's pretty much all open source tech, right? So it's good.
Okay, there was another question by Abdul Samad. I don't know if that's been answered. Do you think building up a database or library when compared to machine learning could be a preferred option?
Yeah, that's a good one. Sorry, I took a while to process it. Yeah, one thing that I realized, and I think indirectly we discussed that when we were talking about the difference between it's going to be whiskey or it's like a stable smell of whiskey. At the end of the day, depending on like the kind of accuracy you're after and the characteristics of the smells that interest you, you might not need a neural network at all. But what I really like about my journey, I guess, is that TinyML allowed me to realize when I might not need TinyML. And yes, for just telling coffee apart from whiskey, just a good old if VOC above blah, then it's coffee. Else, if ethyl alcohol below blah, it's so you could have a database that way or something which is like a stripped down version of the neural network that I have right now, almost to the point where you don't call it a neural network anymore, right? It's just an advanced if then else sort of pattern. But yeah, I hope this answers the question. I think it really depends on how confident you are that you can outsmart the machine. There's a bit of that too. Like it's to some extent, it's actually nice to be able to be like, I don't really know what makes the smell of coffee, like what characterizes the smell of coffee. I could try and figure that out with lots of trial and error, or I could just like put everything in the hands of a neural network, feed the gas sensor readings into that, maybe feed the time of the day, the humidity, the temperature, the weather information, everything that I feel could have an importance, and then do that, right? And if you can afford that on your on the sort of on the class of device you're looking at, then I would say go for it.
Cool. Thank you very much. There are two more questions from Joan and Joe. First, the question of by Joan. Joan, she writes, instead of trial and error with the features, did you try to check the main chemical composition of the whiskey, coffee, etc., and match it with your neural network model, or use it as initial features? It's in the chat. You can also read it up.
It's no, I think you did a good job at retranscribing. It is a really good question. Two things. One is I knew from day one, and like I said, like it's actually in the data sheet of like the sensor I used. It's crappy. I mean, it's not meant to be super accurate. So even if I knew what were like the precisely some of the key chemical compounds in, say, coffee and whiskey, uh, I wouldn't have been able to do anything useful with those because it's unlikely that the sensors would actually like pick them up and and tell them apart from other compounds. What the sensors what the sensor I used do is more like in general they give you a sense of how much nitrogen dioxide there is in the air, but in the meanwhile this particular NO2 sensor might also pick up some slightly related gases like O2 or others, right? So there's that, and but now if I were to improve the nose, which I will. Like I'm really interested in adding more gas sensors. I will look for sensors that are more precise, that are for different gases too, like something that I don't have right now. Although indirectly, to my point before, some of the sensors I already have might be able to pick up ammonia and methane, but I would like to have a sensor that is like specifically dedicated to ammonia, methane, maybe ozone. So adding those to the design, and particularly, and to I forgot the name of to Joe's question, I think, particularly since now I've actually done some reading, which I like I and sadly I only found out a couple of weeks ago, but I found a really good paper that looks at the smell and the fingerprint of burnt popcorn and burnt waffles, interestingly. And it's a paper from about 15 years ago. But one thing that they say, and it's really good to know as a starting point, is if you care about smelling essentially burning food, then it's all about ammonia. So it's good to know, right? Because my trial and error approach, it probably would work with the crappy sensors that I have right now. But feature extraction wise, to the initial question, it's actually good to know that if I really, really, really care about burnt food, I'd rather get myself an ammonia sensor, right? So which I will, because it's some of them are actually quite cheap, and it should be a great addition to the mix.
Great. And one last question from Joe. He says, great, or he or she, sorry, great talk. I'm wondering if one can somehow standardize it and build a repository of smell signatures, like in remote sensing for plant detection or similar repositories.
That's the actual conclusion to that article and to that piece I wrote for Make Magazine in good open source spirits. Yeah, sharing the design of the 3D enclosure was one. Sharing the entire firmware with the graphical user interface is another. But if we can get to a point where we, as like a community, I guess, and an industry, can have similar databases than what we have for image recognition and for video classification and whatnot, that would be really cool. So feel free to like if you want to chat more, Joe. I'd love to chat with you about that. And yeah, I think it could be really cool.
I think Abhijit has some advice. You could use Pimoroni Environ Plus hat to detect NH3. And he also suggests a YouTube of smells like that.
Yeah, or a Shazam of smells, or yeah, mix of but yeah, Abhijit, I think whatever sensor is on this Pimoroni hat, I think I ordered in a different form factor, and it actually should be with me Thursday. So maybe on Thursday you will see me on social media be all about, hey, I can now detect burnt food. But yes, NH3. Like for all of you who are interested, I guess, in investigating further and in maybe replicating and building the nose, if one of your interests is around burnt food, one way or the other, just know that NH3 is an interesting one to have on the radar, because it's ammonia / NH3 is important.
Cool. I see no further questions. Last chance to type in your question in the chat. At a real event, we could have combined this with a whiskey tasting or rum tasting or something. That would have been nice. But
yes, indeed.
Yeah. But I got so thirsty that I poured myself a glass of whiskey.
Yeah, I only have ethyl alcohol, so that's nope. That's a big no. All right. Well, thanks for having me. I think yeah, we shared the contact details before, so to everyone watching either like live tonight or watching the recording, feel free to ping me on like various social media, or even better, like if you end up building the nose or parts of the nose, you don't actually need the 3D enclosure, right? You just need the sensor and the weird terminal. If you end up tinkering with it, find bugs, issues, etc., it's all on GitHub, right? So you can send pull requests and open issues. So I would love to see that coming in.
Great. Thank you very much, Benjamin. There's a lot of praise in the chat. I hope you can read all that. And
Yes.
yeah, thank you very much. Thanks a lot to the audience for watching and following and asking a lot of really, really nice questions, really good questions. And I hope to see you next time. Probably not as a physical event yet, but we'll get there eventually. Have a good night and goodbye. Thank you very much.
Cheers.
Cheers.